We'll go from current slide. And good afternoon. It's, I think, 12:22 or something like that. It's supposed to be Cal 3. It's supposed to have been going for about 7 minutes now. I've been waiting for someone to show up, and so far no one has. So I'll go and get started by myself. Okay? I don't know if you'll hear this in time for it to make any difference, but usually I'm here on campus Monday through Thursday. Sometime like a little before 8 to 8 o'clock, something like that, until 8:30 when my first class is. But yeah, I mean, in my office about those times. So I go up to class a little bit early to get set up. Well, tomorrow is my third day that I'm making up 45 minutes I missed in class last Tuesday. We made up 15 minutes on Tuesday, 15 on Thursday, and tomorrow will be the last 15 that we have to do. And that will be, even though I get here, sometime a little before 8, I won't be in the office at 8:15 because I'll be starting my class then. So shortly after I get to the office, I'll be going up to class. So I won't have much time in the office at all tomorrow morning. But that aside, that'll be the last time that adjustment will need to be made for a while. There is one other announcement. I forgot to say it to my first two classes, but let me go and remind you. This Friday, I do have an infusion, so I will not be on campus, either campus at all on Friday. I will be have to take 4-hour sick leave on Friday. So anyway, just to let you know, if you're looking for me next Friday, not going to be on either campus. All right, we are in chapter 13, functions of several variables, page 898. This is section 13.3, partial derivatives. This is the heart, I think, of this chapter, or at least the beginning of the heart of it, and we'll do some more things with it later, but this is the real key here. So we've been doing some finding partial derivatives, and here was example 6a. This is where we left off last time. To find the partial derivative of f, which is a function of 3 independent variables, xy plus yz squared plus xz, with respect to z. In this case, we consider both the x and the y to be constants to get the derivative with respect to z, the partial with respect to z. So the partial, and that symbol represents partial derivative, the little curly Q d rather than the regular d. Regular d would be a plain derivative, which is of one variable only. This is partial with respect to z. This first term has no z in it, so it's like x is a constant, y is a constant. It's just a constant. Constant times a constant is a constant. Derivative of a constant is 0. So nothing there. Derivative of the second term with respect to z would be, treat the y as a constant, and that would be 2 times y times z to the first power. So 2yz. And the last term, you treat the x as if it's a constant. Derivative of some constant times z would just be the constant x. So there's your first one. Why they did the work for you, I don't know. I guess they're going to do it for B too, so I'm going to do B, okay? Find the partial derivative of f of x, so there's the B part, f of x, y, z, okay, is equal to z times the sine of xy squared plus 2z, all the argument of the sine, plus the sine of xy squared plus 2z. Same argument if I'm reading it right. Yeah. No, I'm sorry. I went reading too far. That's all the... Let me make sure I copied it right, because I was going back and forth on the page. Z sine xy squared plus 2z. Let's do that with respect to z as well. And again, we'll treat x's and y's as if they're a constant. Well, here we have a product rule because sine has z in it as a component. Z is itself. So what's the derivative of a product? Well, it depends on which way you do your thing. It really doesn't matter. You could do the first, which is z, times derivative of the second, which would be a cosine of xy squared plus 2z, times the derivative of the inside, chain rule on the second part, and that's just going to be times the 2. Okay? So I'm going to put the 2 out front. Plus the second times derivative of the first. So the derivative of the first is just 1. So it's just a second. Sine of xy squared plus 2z. That should be our answer. Let's see what we got. 2z cosine xy squared plus 2z plus sine of xy squared plus 2z. Done. Okay? Let's go on and do the c while we've got room to find the partial derivative of this one. Here's a fourth function f, which has 4 independent variables: x, y, z, and w. Okay? And to find and we're going to define this function to be x plus y plus z over w. Okay? Now to find the partial of that f with respect to w, the toughest one to do here, we treat the numerator as if it was a constant. The x's, the y's, and the z's all are constants. And to do that, that would be a constant times w to the minus 1, which would be a minus that constant, x plus y plus z, times w to the minus 2. So put that over w squared. Okay? And that's about the simplest way to write it. You could write it as minus x minus y minus z over w squared. That would work too. They put the constant out in front, and that's exactly. I'm sorry. This morning, I started getting all this congestion. I thought it was because I had the heat on too much, but now it feels a lot more comfortable. But they've had it on a little bit before, but it just seems like it's circulating some sort of allergens that is making my whole head clog up. So sorry about the hacking and the coughing. But anyway, let's go back and see how they do the B and the C part. So there's the A part. We talked through that one. They showed us the answer already. Here's the B part. The partial with respect to z of z sine xy squared plus 2z would just be z, the first, times the root of the second, plus the second, z, all that stuff, times the root of the first, which is partial with respect to z. Well, the first would be a z times cosine x y squared plus 2z, and then chain rule for the z part, and that would give you times 2. Whereas the second part, derivative of z with respect to z, partial of z with respect to z, is 1, so that would just give you sine x y squared plus 2z. And then to move the 2 out front with the z, they just write it as 2z cosine x squared plus xy squared plus 2z plus sine of xy squared plus 2z. Okay. And then the c part, to find the partial of a 4 independent term function, f of x, y, z, w, when that is x plus y plus z divided by w, and you're taking the partial of the f with respect to w, consider the x, y, and z to be constants. So basically you have a constant numerator over a w, which could be the constant numerator times w to the minus 1. So take the root of that is minus 1 times that constant, x plus y plus z, divided by w squared. And that's exactly what we got. All right. Now let's move on to higher order partial derivatives. And hopefully this is going exactly as you would expect it to, but you might find some fairly interesting little twists to come out of this, which tends to make life a little easier, than what you might expect. So, if here you have a function, z is equal to some function of x and y, so two independent variables, one dependent variable. That function has the following second partial derivatives, more than one, okay? More than one. So, here's the first. What if you had derivative with respect to x the partial with respect to x of the partial of that function with respect to x? Well, that would just be second partial of f with respect to x. Just like it would have been if it had been a function of one variable x alone. The other way you can write this is f sub xx, where each x represents partial with respect to that variable. Okay? Now, you could have also, that same function, but taken the partial, differentiate twice with respect to y, and that would have been just as if y was the one independent variable. I'm so sorry. The partial with respect to y of the partial of f with respect to y would be the second partial of f with respect to y. Or, the shorter notation is f sub yy. Okay? Or, we could have differentiated first with respect to x and then with respect to y. That's legal too. So, the partial with respect to x of f is partial of f with respect to x. Take the partial of that with respect to y, and you get the second partial of f with respect. Okay, now here's where things are a little strange, but true. If you look at your nomenclature here, the way we write that, you're taking the partial of the partial of f, that gives you second partial with respect to f, of y after you've taken the partial with respect to x. So the partial with respect to x, partial of f with respect to x, came first, then the partial of that answer with respect to y. Just like it would have been if you had written them separately like you see here, and then just changed the numerator second partial to a square. But, on the other hand, this one right here would have been, I'm going to rewrite this as partial, and this is mixing them up, which you really probably shouldn't do, and that would have been f sub x, right? Well, what that would have been is f sub x, partial with respect to x, and then take that partial with respect to y, and that's how they got this, which, notice the x's and y are reversed from what they are here, because here you're taking the partial with respect to x first, then taking another partial of that partial with respect to y. Here you took the partial with respect to x first, and then took the partial of that with respect to y. So you see these two do produce inverse kind of operations. Okay, you're doing the same thing, but the nomenclature, the way you write it, looks different, because it is. Okay, and then the fourth way you could differentiate with both x, the function with respect to both x and y, is this one. Sorry. The partial with respect to x of the partial of f with respect to y, that would be just like you did. You combine these two partials and make them partial squared, just the way you write that. Second partial of f, first with respect to y, and then with respect to x. Just the same way you write the order the other way. But what's different about it is the partial of the one you do first here, partial with respect to y, you put the y right by the f, because that's the partial you did first, and then you do the partial of that result with respect to x. So that's reflective of what's going on. Now, these last two, the third and the fourth cases, third one from the bottom of that one, and the fourth one here, these are called mixed partial derivatives because you're doing one with respect to x, one with respect to y, one with respect to one variable, one with respect to the other variable. The other two were both with respect to the same variable, so they came out pretty much what you would expect. These, however, you have to be careful of the order, except for the fact that in most cases those two mixed partials are the same. Okay, so I think we're ready for example 7. Find the second partial derivative of the function as a function of x and y of 3x squared, 3xy squared minus 2y plus 5x squared y squared. Okay, and then determine the value. So I guess they want all the second partial derivatives. Okay, and then determine the value of f sub xy of -1, 2. So I think they want them all. So let's start with f sub xx. Well, in reality, you start with f, okay, and f sub x, okay. All right. So f with respect to x would be, treat everything else as a constant, and you just got a single variable x there. Sorry. My head's closing up on me again. All right. Try to keep trucking here. Okay, partial with respect to x would be treat the 3 and the y squared as if they're a constant. 3 is a constant, and treat y squared as if it's 1. And the partial of that with respect to x would just be 3y squared. The constant, because the constant times x, the derivative of that would just be the constant. And then the next one doesn't contribute anything because y is a constant, -2 is a constant, the partial of a constant is 0. Okay, so that doesn't get into the picture. And then the next one, since we're taking with respect to x, that would be 5 times 2, that would be 10x y squared. Okay, now I don't know where the I was just going to say, well, I'm going to have to stop and go clear my head. I can't think where I was heading with it, so let's just forget that. Let me see if I can finish this problem first. So I find the second partial derivatives for the first one that you could get from, I mean, it doesn't matter the order. Let's do f sub xx. Well, this has no x's in it. That has 1, so that would just be a 10y. I think that's the squared. I can't read my writing. So there's your second partial of f with respect to x both times. If you're doing all the partial derivatives, you might want to do your f sub y now, second partial derivatives, and that would be, going back to the original here, that would be 6xy minus 2 with respect to y. That would be 2 times 5 is 10 plus 10 x squared y. Okay? Now, that's your first partial with respect to y. Second partial with respect to y would then be 6x, okay, because the y, these are counted as constants. The y is the one variable, the derivative of that is 1. Okay, derivative of minus 2 is 0, and derivative of this thing, the one variable is y, so that would be a plus 10x. Okay, x squared, sorry. 10x squared. Because the partial of that with respect to y. Okay. Sorry. Now let's do the mixed partials. We've already done f sub x, so now let's do f sub xy, where we're now taking derivative of that with respect to y, and that would be 6y plus 20xy. Okay. Let's do the partial of y then with respect to x. And we've already done the partial with respect to y. It is good to see you, late though you are, although I'm sick and tired of talking to myself. So I'm going to mark you here and then leave the room. No, I've got to go clear my head. I was going to finish this problem first, but what I'll do is let you catch up with what we're doing here. And if you have any questions, let me know when I come back, but I'm going to pause this. I think it stays on the screen, doesn't it? I didn't drink very much, so I think that's dried me out too. But anyway, were you able to follow what we were doing here?
Yes.
Okay.
For the most part.
Okay. So I've gotten down to this far. Did the partial of f with respect to x, and then took its partial with respect to x again. That's what these two lines were. Then we took the partial with respect to y here, and then took its partial with respect to y again here. Okay. Then, it said find the second partial derivatives. There's more than one, okay? With ordinary derivatives, there's only one second derivative. But with partials, you have up to 4 in this case. Okay, so here's the second one. Partial with respect to x the first time, but then take the partial with respect to y of it. Okay, and that's what we did there. And this one, we had taken the partial with respect to y the first time, and now we're taking the partial of this with respect to x. So that's where we'll pick up and go. What is the partial? Yuck. Okay. Of 6xy with respect to x. Partial of 6xy with respect to x. 6y. Perfect. Okay. And then the partial of minus 2 with respect to x. Partial of a constant, derivative of a constant is 0. Okay, so that's a 0. And then the partial of 10x squared y with respect to x would be 20 xy. Because you see, you only reduce that by 1. Okay? And looky here. The partial of x, the partial of f with respect to x, then with respect to y, is exactly the same as the partial of f with respect to y, then with respect to x. Those are identical. So, that was example 7. Now, before we leave, that was just the first part of example 7. Find the second partial derivatives. We just did. All 4 of them. F sub xx, f sub xy, f sub xy, and f sub yx. Finding out that f of xy and f sub yx are the same. Okay? But then it says, determine the value of f sub xy, that's that one over there, at the point -1, 2. So we're asked to do f sub xy at the point -1, 2. So what you reckon that would be?
Are we taking a partial?
We're not taking a partial, we're just evaluating that partial at that point.
Okay, so
6 times 2 plus 20 times negative 1 times 2. Okay, that would be 12. Now count the number of negative signs. 1, so it's going to be a minus. Then multiply those together and you get a 40. And that gives you
negative
38. No, 28, isn't it? Isn't that a 28?
28.
Yeah, negative 28. Or at least that's what I think. In my, yeah, that's what the book got to. Okay? Now, that's my chicken scratch. Let's see how they do it. Okay? Find the second partial derivatives, all of them. That means at least 4 in this case. Begin by finding the first partial derivatives with respect to x and then with y. And that's how we started before. Okay? Partial of this with respect to x is what?
6. Well, the 3x.
Yeah.
6.
With respect to x. Partial of that with respect to x.
6.
Okay. That's with respect to y. With respect to x.
Oh.
Yeah, you treat the y as a constant and take a derivative with respect to x. Is what? 3 y squared. That's the other constant. 3y squared. There we got it. Partial of that with respect to x.
2.
With respect to
Oh,
x.
0.
0, because that's a constant, that's a constant. That with respect to x.
10.
10
10x.
x
Y squared.
y squared. Perfect. And there we have that. Now take the partial of that thing with respect to y. What would that be?
6x. Y.
6xy. Perfect. This with respect to y? Minus 2. Got it. This with respect to y?
10x. 10x squared. Y.
10x over y. Perfect. Okay? So here we got the partial of that thing with respect to x, partial of that thing with respect to y. Now we do a second partial, and we can do this with respect to x, then this with respect to y, that with respect to x, and that with respect to y. Doesn't matter which order you do. Let's see which one they do first. Then differentiate each of those with respect to both x and y. So they're doing it the same way I did. Let's take the partial of this one with respect to x. And you see this one stays together, then you take the partial of this thing with respect to x. And that would be what? Partial of that with respect to x.
6.
With respect to x.
Oh, 3y squared. Right?
Treat the y like it's a constant. 3 times a constant is a constant. And the derivative of a constant is 0. Okay, so that's 0. This with respect to x would be
1.
say again?
Would be 2 and 1.
With respect to x, treat these like a constant.
Oh, 10. 10y squared.
10y squared, yes, yes, yes. You see why?
Yeah, I realized that you're taking that part of the
With respect to that variable, so this is the one that you operate on, you just treat the rest like they're constants. Okay. Now let's take the partial of this with respect to y. What would that be? 6x. This with respect to y. 0. This with respect to y.
10. 10x squared.
Yes, 10x squared. So you treat all that like a constant. And so constant times y, root of that would be a constant. Now, next thing we're going to do is take partial of this with respect to y. Okay? So let's just review that. What would this one be?
The partial derivative, we're taking which one? The y?
Yeah, this with respect to y. So this would be f sub xy. you're doing f sub x, and then taking the partial of that with respect to y. Here's your f sub x. Take the partial of that with respect to y.
But then you'll treat that as a constant, right?
With respect to y.
Just 0. 3y. 3y squared. Oh, 6.
6y. Got it. Plus this one with respect to y. 20 x y. No, just y. You drop that by 1, right? Okay. Now let's take the partial of this one with respect to x. F sub y, take the partial with respect to x. And what would that be? 6. No, taking with respect to x. Y, yeah. Take the partial with respect to y of that. 0. Okay, and the partial with respect to y of this? Plus 10 x squared. Exactly. No, that was 20. With respect to x, yeah. 20x squared. X squared y, I'm sorry. With respect to x, 20xy. Goodness, I don't know where I got the square from. I think I'm listening to you. Okay. Okay. Taking the partial of this with respect to x, be 20x times y. And sure enough, these two are the same. If you ever get them not being the same, which I looked over there and said, hey, they aren't the same, and then I saw where we made a mistake. So, yeah. Now, they're going to do that on the next page. So let's go to it. Partial of that would be 6y plus 20xy, and the partial of f sub y with respect to x, it would be 6y plus 20xy. And those are indeed the same. Now, the next thing we're going to do, goodness, I got to sneeze. Hope I can hold it back. Is at the point. You awake? Okay. Earlier this morning, I was just so hot in here, I couldn't stand it, and now it feels hot and I'm sneezing. I don't know. Like I said. So we want to evaluate this one at the point -1, 2, which is what we did after you came in, but let's do it again. What would that be? Just evaluate at -1, 2.
6 times 2.
2 is
12.
12
Plus 20.
plus 20
1
times the -1
times 2.
times 2.
40.
-40. So 12 minus 40 is -40. That's what you got. Right? Okay. Whew. All right. Now, here's theorem 13.3. What we observed in that one problem, let's see, it seems like that's the case. Equality of the mixed partial derivatives. If f is a function of x and y, just two independent variables, such that f of sub xy, that means the partial of f with respect to x, we take the partial of that with respect to y, and the partial of f with respect to y, and then take the partial of that with respect to x. If both of those are continuous, then on an open disk R, then for every xy, I got to sneeze again, xy in that R, the f sub xy of x and y is equal to the f sub yx of x and y. So it doesn't matter which order, sorry. Doesn't matter which order you take the partials. If they're mixed partials, it doesn't matter, okay? I'm sorry, this is a weird day. I don't know what's going on. One possibility is we turned on our heat for the first time last night. And I don't know about in your house, but at our house, things get a little dusty over summer and winter, anytime. And when you turn it on the first time, you get dust particles get heated up, and so that may be what's going wrong with my head today. I don't know. So anyway, that's true. If both of those derivatives exist and are continuous on an open disk, then that's the result. Sorry. Now, this theorem applies to a function f of 3 or more variables as long as the second partial derivatives are continuous. For example, if you have w, let me write this down. I thought they were going to put it on the slide, but they didn't. W is some function of both x, y, and z, okay, function of 3 variables, and all the second partial derivatives are continuous on some open region R, then at each point in that open region R, the ordered differentiation of the mixed partial derivatives is irrelevant. If the third partial derivative of f is also continuous, then the order of the differentials in the mixed third partial derivatives are irrelevant, as long as they're all taken to the same order. And I'm sorry, I'm going to have to go into my head. I can't breathe anymore. So let me pause this again. So here we have w, an independent variable, as a function of a dependent variable as a function of 3 independent variables. And that all the second partial derivatives are continuous in open space. Okay. I think we already said all that. So I think I was ready to go to example 8. Is that on here? Yeah, here it is. All right. So here we have a function. F sub x, y, and z is equal to y e to the x plus x log z. Okay? That's a function of 3 independent variables, x, y, and z. Now, we're to show that f sub xz is also the same as f sub zx. That's the first one. Then we'll show that f sub zz is equal to f sub zxz, and that's also the same as the partial of f sub zzx. Okay? Now, these two, it's pretty obvious. Those are the same variables taken the same number of times, right? These, you've got to make sure you got 1x and 2 z's. 1x and 2 z's, 1x and 2 z's. The order changes, but the partials should be the same. So how would you begin to show those things they're asking for? What would be the first step? You have several first steps you could choose from, at least 2. What would be your first step?
I would say derivative.
Yes, which one?
Fx.
Yeah, why not? Let's do f sub x. So let's start there, f sub x. And what would it be? Y. Why not? Say again?
YZ.
Where did you get that?
From taking a derivative of fx.
Yeah.
Y.
Y e to the x. Okay? The reason for that, if you're taking a partial with respect to x, you hold the y like it's a constant. So like the 7 or 43 thirds or whatever, okay, times e to the x. Well, a constant, derivative of a constant times a function is that constant times the derivative of that function, and derivative of e to x is e to x. The beauty of the exponential function is derivative and its integral is itself. Okay? So yeah, that's the first term. F sub x. How about the next term?
Plus.
Plus. Log z, exactly, because that's a constant. Z is a constant. Treat it like a constant. And you got x times a constant, which is the same as a constant times x, and derivative of a constant times x is just a constant, which is log z. Okay, what's the next step you want to do? You got, again, several choices. I would say 1 or 2 choices here. No, you really only have one choice. What you want to do next? Well, no, you have 2 choices for sure.
Could I take the derivative of f of y?
Okay, you could, but why would you want to? I mean, in other circumstances, yes, but what we're looking for is f sub xz, f sub zx, f sub x, zz, f sub z, x sub y. You're not going to take an f with respect to y anywhere in there. So, yeah, let's not do that. We could. It's doable, but why? We're not looking for it.
So it'd be f of z.
F sub z. Okay, let's take f sub z. The partial of f with respect to z. And what would that be on the first one? Huh? There is no z in that. So you treat y as if it's a constant, x as if it's a constant, e of a constant is a constant, y times constant times a constant is a constant, derivative of a constant with respect to z is 0. Okay, so that's done. How about this one? X. Nope. Taking derivative of log z. What's the derivative of log z? Absolutely. X over z. Okay. So there you got your 2 first partials. You don't need one with respect to y because they didn't ask for any. Okay? You could take one, but they didn't ask for it, so that we're not concerned with there. So now you've got 2 choices. Well, only one choice of what you do with this one, and you got 2 choices of what you do with that. F of xz. Now that will give you exactly what you want here. So let's see what we got.
Would be
1 over z, and that is all, folks. Because this is just a constant. Derivative of constant is 0. This is log z. Derivative of that with respect to z is 1 over z. Okay, what you want to do next? You got, again, at least 2 choices. Nothing. Okay, f sub zx. Ooh, I can't write. Okay. Ah, it didn't take. Okay, now f sub z x. So the partial of that with respect to x. 1 over z. You're absolutely right. And looky here, these 2 are indeed equal to each other. Okay? And that's the first thing it asks. Yep, we got it. The next thing it asked, though, was then to do, and you got 2 choices here, actually 3 choices here. Yep. What you want to do next? F sub zz. Okay, we haven't done that one, so F sub zz, and that would be what? We need it for right over here, so what would that be? X with one other little thing to do to it. Why that? Because what?
We don't need the x.
No, no. Okay, wait. I'm going to rewrite this as x z to the minus 1. Yeah. And then when you take the derivative partial of this with respect to z again, the x is a constant, so leave it alone. That'd be minus x z to the minus 2. So that's where you need the minus here of x over z squared. Okay? Now, okay, you've got 3 things left to do, and you need to do all 3 of them. So it doesn't matter which order you do them. What would you get? What's one of them you want to do first?
Let's go for f of x.
F of x?
Yeah, f of x,
zz. Okay, we're going to do this one. Okay, so f sub x z z. You take the partial of f sub x z, which is this, with respect to z, and what do you get?
1 over minus.
With a minus sign. Because think of that as z to the minus 1, and the derivative of that would be minus z to the minus 2, which is minus 1 over z squared. Got it. Okay? Next.
F over zx.
F sub zxz, is that what you said?
Mm-hmm.
Okay, we're going for this one now. Okay, good. What would that give you?
Minus
Yep.
1 over z squared.
Yep. Got to be. Same, got the same as that, so it better be the same. Yeah. And then what's the last one we got to do? F sub z sub x. Got it. And what would that be? Minus 1 over z squared. Yeah, look at that. All 3 of those are equal because you had the same subscript, just in different orders. So, yep, they're all the same. Perfect. So you proved the first 2 there, and then the last 3 there. Okay? These are equivalent. These are equivalent. And these are equivalent. Okay, so yeah, everything's equivalent. Good deal. All right. That was example 8, bottom of page 899. Got it? Okay. I'm going to clear my scratch, and let's watch how they do it. Okay. First they did the 2 first partials, just like you did. The partial of f of x, y, and z with respect to x was y e to the x, just the same as that, plus log z, because you're taking the partial with respect to x, and this is treated as a constant. Y is treated as a constant, derivative of e to the x is e to the x. Okay? So that was the partial with respect to x. Partial of that thing with respect to z, this would give you nothing because there's no z's in it. So that's just treat it like a constant. Partial of a constant is 0. Okay, derivative of a constant is 0. And the second partial of this with respect to z, so we're doing with respect to z, x is a constant, derivative of log z is 1 over z. So that gives you that. Now, they didn't ask for either one of those, but those are first steps you got to do at some point or another. Okay. Now, I think they're probably going to do the same thing you did. They're going to take the partial of this with respect to z to get the first thing there. Take the partial of z with respect to x to get the second thing. And let's see if that's what they do. Okay, second partials, note that the first 2 are equal. The partial of x with respect to z, this partial with respect to z now, that gives you nothing, and this gives you just 1 over z. The partial of z with respect to x, this with respect to x, that gives you 1 over z. So treat z as a constant, but it would be 1/7 of x would be 1/7, or whatever. So that's 1 over Z2. Those are exactly the same. Now we do need another second partial. We got that done, This one we'll get from here. This one we'll get from here. But this one, we need the partial with respect to ZZ to get that last one. So let's do that. The partial of Z with respect to Z would be a minus X over Z squared. Think of this as XZ to the minus 1. Take the partial with respect to Z would be a minus X to Z to the minus 2. And that would be minus X over Z squared. So yeah. So what now? We showed, notice these two are equal, and that's what it said, show that those two are equal. We just did. Okay? Then to show the last part, we want the partial of this with respect to Z, the partial of that with respect to Z, but the partial of this with respect to X. So that's the next series of steps in whatever order you want to. So the third partials, and you don't need to do both of these, but you can. Partial of this one with respect to Z the second time, think of this as Z to the minus 1, that would be minus Z to the minus 2, and that's it. And it's the same as this, so that would be the same result. But the partial of this with respect to X would be, this is a constant, and that's X to the first power, root of that is 1. So you just get minus 1 over Z squared. All three of those, right? Yes, we showed it. All right, that was example 8, bottom of page 899. And that was the last one in the section. So homework exercises here. Do any of the odds 5 through 9, they're all at calcchat.com. And all the answers in the back of the book too. Then the next group, a huge group here, any of the odds 11 through 39, okay? They're all at CalcChat, 13's at CalcView. Then do either 41 or 43, they're both at CalcChat, 41's at CalcView. Do any of the odds 45 to 51, they're all at CalcChat, 45's at CalcView. Do either 53 or 55 or both, and they're both at CalcChat, 53's at CalcView. Do any of the odds 57 to 61, they're all at CalcChat, you could, 57's at CalcView, goodness gracious. All of 57 to 61, the odds 57 to 61 are at CalcChat, 57's at CalcView. Then do any of the odds 63 to 67, they're all at CalcChat. Any of the odds 69 to 75, they're all at CalcChat. Any of the odds 77 through 85, they're all at CalcChat, but 79's at CalcView. Do either 87 or 89, they're both at CalcChat. Either 91 or 93, they're both at CalcChat, but 93's at CalcView. Do either 95 or 97, they're both at CalcChat. Either 99 or 101, they're both at CalcChat. Do 103, it's at CalcChat. And do 105, it's at CalcChat. And by the way, that refers to the Cauchy-Riemann equations. And that might lend itself to a couple paper topics. Who was Cauchy? Who was Riemann? You've already turned in your paper, right? Yeah, but this is for people listening at home. If anyone's listening at home, those are some Cauchy-Riemann equations. So you can write about either one of the people, Cauchy or Riemann. Cauchy, I think, was French, and Riemann, I'm pretty sure, was German. Excuse me, that also possibly, how did Cauchy go about arriving his, and then how did Riemann either improve on those, work on them, extend them, or whatever, or did they work on them together and just get both their names out? They usually, most of the time back then, they named after one, and then someone came along and did a little more work on it to expand it or extend it to other applications, so we would name both of them. Okay, and then do 107. It should be at Calc Chat. And then there's exploring concepts, 109 and any of the odds 109 to 113. They should all be at Calc Chat. Then there's some application problems. You can do any of the odds 115. Ooh. It looks like 115 to 131. They should all be at Calc Chat. Now you can break them down and do one or two of each group if you see multiple groups there. Okay. And that finishes 13.3. Any questions? Okay. Then I'm going to move on to 13.4. Okay. All right. Okay, that's all that sneezing I was doing. Knock on my head. They're all congested and achy feeling. All right. All right. Let's go to current slide. We're still in chapter 13, functions of several variables. Now we're going to talk about differentials. Now when we were talking about differentials when we did derivatives, what basically was that? If dy dx was equal to 3x, what would that be in differential form? Yeah, dy dx is equal to, say, 3x squared or something like that. How would you write that in differential form?
Just dy was something like that.
Okay. Now these are ordinary derivatives, not partials. Okay, just so you understand what I'm saying. Let's see. Ooh, let me get my pen back. Okay. Dy dx is equal to 3x squared. I don't know if that's the only one I say, but written in differential form, this would be dy is equal to 3x squared dx. Remember that? Okay. It's sort of like, though you're not supposed to say this in pure math, that you multiply both sides of the equation by dx. You're not supposed to say that because dy dx is an operator, or d by dx is an operator operating on the function y. So you can't multiply by part of an operator. But it sure is what it looked like, okay? So we just call that writing that in differential form, okay? Now, with that in mind, let's look at our objectives here. I thought we were going to get right into it, but I forgot. We have to look at our objectives. Okay. Oh, man. First, we'll understand the concepts of increments and differentials. Okay. Increments being delta x's and differentials being dx's. Okay. So, kind of that concept. We'll extend the concepts of differentiability to functions of two variables. You know, I was thinking we already did that. Okay, but we'll get into a little deeper there. And we'll use the differential as an approximation. And they really love doing that. And I guess it's a fair thing to do. Okay? So let's look at increments and differentials. Let's say we have a function. Now we're going back to, like I just did, ordinary derivatives. Okay, not partials for now. Then we'll get down to it later. Not here, but later. For y is equal to f of x, the differential of y was defined as this. dy is equal to f prime of x dx. Now, if you rewrite this as dy dx is equal to f prime of x, it just seems like it's redundant. It's two ways of writing the same thing, right? But now we're writing it as a differential. dy is equal to f prime dx, which, if you think about it, in Cal 2, we would then take the integral of both sides, and this would be y, and this would be some function of x. In fact, it would be f of x, plus some c, unless it was a definite integral. Okay, indefinite integral, it would be a plus c. Similar terminology is used for a function of two variables. Z is equal to f of x, y. Okay, this is the two variables. That is that the delta x and the delta y are increments of x and y, and the increments of z is delta z. So, okay, I don't know if you remember my little arm waving before. Okay, if this was the x-axis and this was the y-axis and this was the z-axis, right? Right-hand rule that works. Okay. So let's say we have an xy somewhere right here. The x is 1, 2, 3, 4, 5 blocks this way, and the y is 1, 2, 3, 6 blocks this way. So this is 5, 6 down here. Here's your z up here, okay, that corresponds to f of xy, right? Now let's do x just a little bit further here, so it's x plus delta x. Your y just a little bit further here, so it's y plus delta y. Now you're at a new point, delta z. Okay? And what is that delta z? Well, it's the change of z. Z, the new z was here. I said delta z. The new z was here. The old z was there. Right? So the delta z is the difference between them. And what's that? That's f of x plus delta x, comma, y plus delta y. That's our new z minus the old z, and that's your delta z. Okay? So this is merely the difference in z's, where the bigger z was with a delta added both to the x and to the y, minus the original z, which is f of xy. So this gave the change of z. Is that clear? Okay? Now, sort of hang on to the thought. That's a way to talk about the increment in z, a delta z, how it changes incrementally. Change x and y incrementally, and what that changed from the f of xy before, that's your delta z. Okay, that's your increment of z. Now, here's your definition of a total derivative. If z is equal to some function of x and y, delta x and delta y are increments of x and y, then the differentials of the independent variables, x and y, are dx is equal to delta x, or at least the limit of delta x, as delta x goes to 0 is dx, and the limit of delta y goes to 0 is dy. Okay? The differentials of those independent variables are the dx and the dy, which correspond to the deltas, they're not quite the same. And the total differential, if you go back to what we did before, where we had a delta z, okay, the total differential would be of change of z now, up here, would be the partial of z with respect to x times the dx. This is a dx now, just like this was. This is partial of z with respect to y times dy, which, the other way to say it was f sub xy. Remember, f and z are the same, right? So it's partial of f with respect to x dx plus the partial of f with respect to y dy. Okay? Now, the other way of looking at this is the change of z with respect to x, the change of z with respect to y, that's our total change of z. Or the change of f with respect to x times dx, if we change of f with respect to x, this is the change of f with respect to y, so is that it together with the total change of f, which is your So they kind of make sense. These are different, these are increments. This is your total differential. Okay? This definition can be extended to a function of 3 or more variables. It just goes on and on and on. Let's say 4. W is equal to alpha of x, y, z, and u. This is independent or dependent variable. These are all 4 independent variables. Then dx is delta x, dy is delta y, dz is delta z, du is delta u. Those are the independent variables. And the total differential of the dependent variable, dw, is the partial of w with respect to x, dx, plus the partial of w with respect to y, dy, plus the partial of w with respect to z, dz, plus the partial of w with respect to u, du. Okay? That's how you get your total differential. Okay? Now, you could have said that with F's here. The change of w would be the partial of f with respect to x, dx, plus the partial of f with respect to y, dy, plus the partial of f with respect to z, dz, the partial of f with respect to u, du. And those, of course, could have been f sub x dx plus f sub y dy plus f sub z dz plus f sub u du. Okay. Lots of ways to write them. They all mean the same thing. Okay. Now, here's example 1. Find the total differential for each function. What do you reckon this total differential? What's the name for it? dz. That's the differential of z. Okay, and what would that be? Write it down for me, or say it out loud and I'll write it down. Partial of z with respect to x dx plus partial of z with respect to y dy. Now again, that should sort of suggest to you what we're talking about here. This is how much z is changing when you change x a little bit. This is how much z is changing when you change y a little bit. And then this would be the total of how much you change when you change them both. And those are differential of z. Okay? Now, can you take dz dx? Partial of z with respect to x. What would that be? Okay. Take the partial of z with respect to x. First term. A little louder. 2 for sure. 2 what? There is no z up there. No, you're taking partial with respect to x. See? No, don't take the partial of that. It's treat that as a constant. 2 sine y. Oh my goodness, you got here in time. For the end of class, okay. Glad you're here. Justin's here. Let's see, how much time do we have? Oh, I don't have my watch out. Thought I'd had it out. Oh, we got 10 minutes or so, close to 15. Okay, that's the first part. 2 sine y. You're taking the partial of this with respect to x. The first part of that is just you treat the y as a constant. Take the derivative with respect to x. That would be 2 sine y times the derivative of x would be 1. Okay? But we haven't done the second part of it. What's that? Partial of that with respect to x. Y squared. Perfect. That's your partial of z with respect to x, so that's what we multiply by dx. Okay? Plus, now what do we do?
You make it the first time, right?
What's that?
Are you making it the first time with the 2x?
Okay.
So you set it up.
You're doing what though? Partial of z with respect to y now. You're doing this thing to this function, and then going to multiply it by dy. So what would that be? 2x cosine y. Perfect, perfect, perfect. That's the first part anyway. y0. Plus, okay, how about that? Wait, where'd you get a plus? Minus, 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 minus. Okay, so I don't buy that. Okay, so minus 6x squared y. Why not? Okay, and that's time dy. Got it. I think we have it. Okay. Find the total differential for each function. There it is for the a function. Let's do it for the b function. What will that look like? dw is equal to say that again. No, in differentials we don't put them over. We put them, yeah.
So it'd be dw.
Okay. Oh. Okay, you're saying d. If you've been saying partial, I got it. It's equal to partial of w with respect to x. Is that what you're meaning?
Yeah.
Yeah, those are partials, okay? I thought you were talking about here for me to continue here and put it over. Okay, got it. Then that's times dx. That is not a partial, that is a dx. Next. Plus partial of w with respect to y. Whoops, I say y and write w. What's wrong with me? Times what? We already got the partial w with respect to y. You may not be able to read what I'm saying, but dy, you got it. That's the dy, and that is a d, not a partial. Okay, next. Well, with respect to z, times dz. You only call it d when it actually is a d. The other things are partials. Okay. All right, so that's what it is. But you tell me what that translates to be. dw is equal to, what is partial w with respect to x? 2x dx plus 2y dy plus 2z dz. Now that's way too regular looking thing, but that's exactly what your partial is. Okay? You could actually pull out the 2, say it's equal to 2 times x dx plus y dy plus z dz. Don't know that it's any easier, but you could do it. Okay? But they leave it just like that, I think. Okay. All Oh, let's erase my chicken scratch and see what they got and see if we got the same thing. All right, first, goodness, I'm running out of energy fast. I think part of that was eating much too fast and not drinking enough too fast. Because I ran out of time. Total differential of z here for that one is dz. Now that's a d, not a partial. dz is equal to, take the partial of this with respect to x. And that's just going to be, well, it's partial of z with respect to x dx plus partial of z with respect to y dy. Okay, that's what it is. Now we take those partials and fill them in. Okay. Oh, goodness gracious, I'm tired. All right, so the dz would equal to, first we'll take the partial of z with respect to x. 2 sine y minus 6x y squared. Take the partial of that with respect to x. You see that? Okay, you want to hear when we did it. And that's times your dx plus the partial of z with respect to y, which you treat the x as if it's a constant, so it's 2x, and the derivative of sine y is cosine y. And then you take the partial of this with respect to y, and that would be a minus 6x squared y. That's in parentheses times dy. Okay? So, there's your partial, your total differential of dz, of z. Okay. Now we'll do the b part, which is total differential dw for that w. And we write it down just like we did before. Total differential will be the partial of w with respect to x dx plus the partial of w with respect to y dy plus the partial of w with respect to z dz. And you see that this form, to me, indicates what you're doing. If you think of these as canceling out, that's the partial with respect to w, but you also do that partial with respect to y and that partial with, so you got to change the w, change the w, and change the w, and the total is going to be that change of w. This is the total differential. There's a partial with respect to x, a partial with respect to y, a partial with respect to z. Your total is adding those three together, and that's what total is. Okay? I don't know if that's helpful or not, but it helps me remember. Now all we got to do is do what partial w with respect to x is. And like you did before, that's simply 2x dx plus 2y dy plus 2z dz. So the partial w with respect to x is 2x. The others are constants, so that adds zeros to it. Plus the partial of w with respect to y. The x squared gives you nothing. The y squared gives you 2y. And the z squared gives you nothing. So that's 2y dy and then 2z dz.
Could you write that as dw equals 2d times x, y, z?
Okay, say that one more time.
Could you write that as dw equals 2d times x, y, and z?
Okay, you're saying write this as dw equal to what?
2d.
To what?
2d.
2d?
And just multiply with the x, y, and z.
Is that what you're saying?
Yes. Or would I give you, would I not give you the same result?
I don't think so. Yeah, because I'm really not certain what that stands for. It looks like d of x, y, and z, the product of x, y, and z, or that's sort of a made-up nomenclature. So, no, let's not do it. Okay, this is what that stands for. Okay, just because that's your w, whatever your w is, that would be. This is the generic form for whatever w you have for that particular w. That's one and only. That would give you this. Okay. All right. So that was 1B. All right, the next topic here, and we just have time for it, is differentiability. Okay? We won't be able to get far in it, but let's at least introduce it. Oh, boy. For a differentiable function given by y is equal to f of x, now we're going back to derivatives, plain, ordinary derivatives, single variable. Okay? Y is equal to f of x. You can use the differential, and we already said this before, dy is equal to f prime dx. Okay? That's what we have. As an approximation for small delta x's of small delta y's, which delta y is f of x plus your delta x minus f of y, minus f of x. So going back almost to your derivative formula, not quite, but close to it. Than that. When a similar approximation is possible for a function of two or more variables, the function is said to be differentiable. Okay, so if that approximation can be made or something similar to it, then we say this is a differentiable function. So that's stated explicitly in this definition. A function f given by z is equal to f of xy. So right now we're sticking with two variables, two independent variables, one dependent variable, is differentiable at some point x0, y0 if the delta z here can be written in the form of delta z is equal to f sub x, that's your partial of f with respect to x, at that particular point x0, y0 times delta x, plus the partial of this f at that point x0, y0 times delta y, plus some epsilon 1 that refers to how far you all are off here, and epsilon 2, which is how far you all are off there, where both epsilon 1 and epsilon 2 are approaching 0 as delta x, delta y is approaching 0, 0. Now that's the change of x, not x. The change of x, comma change of y are both approaching 0. The function f is differentiable in a region R that is differentiable at each point in R. Function f is differentiable in a region R if it is differentiable at each point in R. Okay? So it's kind of a different approach to differentiability. It has some of the same characteristics a little bit, but again, you got multiple variables, so you have a lot more terms in them. Okay? Here's example 2. The question is, are we going to have time for it? What you think? How much time we got? How much? 3 minutes. I'm kind of guessing no. Okay? So we will begin next time at example 2 here. And we got just a little bit done in this section. So I think you can do any of the odds 3 through 7. They're all at Calc Chat, 3's at Calc View. And we didn't quite get far enough to do using the differential as an approximation. So we'll pick up there next time. So you got a few exercises, quite a few from 3.3 and then just a couple more from 3.4. Make sense? I mean 13.4. 13.3 and 13.4. Any questions? All right. Sorry that I had to stop class a couple of times. My head just got completely congested, and I got a sneezing fit, and then it all started loosening up. So sorry about that. All right.